It's a great pleasure to have Volkan Cevher with us today. Volkan is an associate professor at EPFL, where he runs the Lab for Information and Inference Systems. He's also a faculty fellow in electrical and computer engineering at Rice. And his research quite broadly revolves around signal processing, machine learning, optimization, and information theory. He's really doing a lot of stuff in a lot of areas, a lot of cool work. He's won a lot of several impressive best paper awards and grants. So it's really a great pleasure to have him here with us today, where he will be talking about Minimax optimization. So when you're ready.
So first of all, thanks for the invitation. I wish we had a chance to physically come and visit, but hopefully this will change as vaccinations become more prevalent and we have some better solutions for COVID. I hope everybody is doing well during this really odd times and having a safe quarantine and hopefully normalizing their life. What I'll do today is to talk about a broad class of algorithms that I will maybe ineptly name as Robbins-Monro-type algorithms. And this encompasses two works with my collaborators and my PhD students. So in particular, Panayotis Maktikopoulos, he will be the M in the citations that I give. Yapin C, my former PhD student, Nadav Halak, my former postdoc, who's a faculty at Technion, and Ali Kavish, who's a PhD student of mine. Okay. So we'll start with a motivation from statistical learning theory. So let's think about the supervised learning problem. So I'm going to use the Vapnik's way of setting this up. We have some generator. We have some supervisor. We have a machine learner. So the generator gives us some data AI, the supervisor gives us some labels, and the job of the machine learner is to have a function that predicts BI given AI. Typically, we pick a function class, so H is element of some function class, but what we would like is to use parametric functions such as neural networks, which I will parameterize by this little x. And what we do is try to make sure that our prediction of these labels is as close as possible. For this, we typically pick a loss function. And then what we do is we write down optimization problems. So one of the most important optimization problems is the min type problems. In this particular case, the classical approach of, let's say, the risk minimization is the bread and butter. What we do is we try to minimize this expected risk, or in this case, the population loss, where A and B are generated with respect to some unknown distribution. Right? So one can think of this simply, one can think of this as simply minimization of expected fx theta in the optimizer notation. And what we typically do is have some sort of a finite sum approximation of it. All right. Now, this problem, I think, captures most of the regression classification. And I mean, people made careers out of this formulation, right? So now I'm going to twist, and I'm going to use the same framework to give you an example of min-max type problems. By the way, I apologize for my handwriting. I've never had a good handwriting throughout my life. So if certain things are absolutely unclear, feel free to interrupt and tell me. And I mean, I sometimes make, of course, typos, so let me know if you spot one. So what I would like to do is give you a density estimation motivation. So motivation here is from generative adversarial networks. So the idea is very simple. You know, somehow this generator gives us samples, and what we would like to do is learn a distribution over these samples. So given an empirical measure, mu n, n is the number of samples. What we would like to do is learn a density. And the classical way to do this in statistics is that you assume a parametric density and then you try to learn the parameters of this density. And maybe more modern approach is to parameterize such densities using neural networks. And the idea is very simple. So the parametric density. So what we do is we try to parameterize the density by taking a neural network and pushing forward a simple distribution. All right. So the mechanism, so this particular one is given, something like a Gaussian, and this push forward, roughly speaking, is that you generate, so let's say a random variable with respect to this distribution, and then you push this random variable through the neural network, and then hence you will have a random variable here. Right? This is what we would like to use as a mechanism in, you know, learning the distribution. So the problem here is very simple. So let's try to make it of space here. Out of space. The problem is very simple. What we need is a loss function. One loss function that makes sense is the Wasserstein distance, because you're given some empirical samples. So you have zero support in samples that you haven't observed. So what you try to do is, by the way, just to highlight, you may have constraints here. So I'm going to use calligraphic X to highlight these constraints. So we're going to try to learn the parameters of this neural network in such a way that minimizes the Wasserstein distance between the empirical measure and the push forward measure. Now I'm using the subscripted x1. It will be clear why I am doing this in a couple of minutes. So the Wasserstein distance here is a plug-in estimator, because ideally what we would like to do is use the true measure here to learn our parameters. So we're using basically a plug-in estimator. Now there are pretty bad convergence bounds here in terms of plug-in the empirical measure, but we're going to sweep that under the carpet and try to focus on the optimization aspects. Okay. Now this Wasserstein distance is not smooth. So what we try to do in optimization is we try to put it in a max form to see if we gain any advantage. So there is an easy way to do this. So we have an x1 using Kantorovich-Rubin's duality. We have a max. Now this max is going to be over some functions d that are 1 Lipschitz. All right, so we're going to have some functions d that are 1 Lipschitz. And what we're going to do is we're going to write some inner products. So these inner products actually correspond to integrals. So this is like the integral of this function d with respect to the measure, right? Alternatively, you can write them in terms of expectations and so on and so forth, which I will do. But the point I want to make here is that here the function class D is difficult to represent. So what we do in practice is we plug in another neural network here, meaning we put some parameters x2 here, okay? So we just parameterized, we added another neural network. So this quote unquote dual variable, we're gonna call it the discriminator network, which is parameterized by this. And what we're gonna do is we're gonna write the following min-max problem. Such that, so expectation, so this is interesting. So the data comes from un dx2a minus expectation omega comes from p omega dx2 hx1 omega. So this will be our problem. All right. Now, as you can see, this is in this particular form, min x1 is x1, max x2 is x2, expectation, right? So we're going to have theta x1, x2, theta. So this will be our mini-max problem. All right, is this clear? All right, I'm going to assume it is. Okay. Now, let's think about the solution concepts. All right. To set up the solution concepts in some nice general fashion, I will just do a bit of notation unification. All right. So in terms of the notation, so we're going to go from, note that, we're going to go from min to min max. So in min, hello? Yes?
Excuse me. Yeah, sorry. I wonder if you could just put up the previous slide for a second, please.
No problem.
Thank you. So just looking here, if I wanted to just step to the last line on the slides, I feel like, let's see. So the role of x1 is basically your class of functions that you're applying. And so the x1 is causing those?
Our quote-unquote generator parameters, that is correct.
Oh.
So x1 are the parameter, represent the parameters that we use in our mechanism to generate samples. This is how we parameterize. So if it makes sense, I can just put x1 here. So this is our generator parameters. x2 is actually needs to be constrained as well, because what we need to do, which I swept under the carpet here, it needs to be chosen in such a way that dx2 is one Lipschitz. Otherwise, the problems are not equivalent.
Sorry, I need just a little bit more help here. So, so if I'm thinking about a problem where I'm just going to fit, say, the dumbest thing I can think of, a regression function to some data, but I'm willing to assume that that data are actually coming from some distribution which lies in a ball close to the empirical measure. Let's say that I just took that setup. I assume that fits this framework, and then I'm still a little bit puzzled about x1, x2, and theta.
The x2 is parameters for this function. So you understand the trick that I did here is literally something like this. You know, I have, let's say, x infinity. I'm just writing it as max form d x d one norm is less than or equal to 1. So I'm just doing a trick like this. Okay, this is Kantorovich-Rubinstein duality. So the way we, I mean, I don't know, maybe you know this, I'm unassuming in this point, so let me know if you already know this. This is an equivalent problem as long as this function is 1 Lipschitz. Now, in which norm it is 1 Lipschitz, it doesn't quite matter. You can pick a norm, it just scales the objective value here, right? But the point is that it's some function in this broad function class. We don't know what to do with it, so we parameterize it here with another neural network. And then the parameters of the other neural network comes in. And the distance in which I am measuring this is the Wasserstein distance, which leads to this particular problem. But the original GAN formulation, so here this is GAN, the acronym, it is done with the Janssen-Shannon divergence.
Which of x1 and x2 gives me my regression coefficients in my sort of toy version of the problem?
x1 would be your regression coefficients.
Thank you. So we're minimizing the error associated with my choice of regression coefficients. And then in x2, you're sort of generating these instances that are sort of adversarial, and hence the max.
You can think of it as adversarial. And it actually sounds cooler when we try to cast these things from a game theoretic perspective. But the game theoretic perspective is a bit broader. As you can see, we set the problem up. There is no game here. We have control over both variables. It's just a simple equivalence, just like the example I have here. Does that make sense?
It helps. Thank you very much.
No problem. All right, so what I'll do is a simple unification of the notation. So, okay, so maybe the color. So in the min problem, I'm just gonna put this, but the stochastic version is covered, all right? It just makes the notation a little bit easier. So we're gonna have x in x. In Minmax, right, so we are considering x1 in x1, max x2 in x2, f of x1, x2. So again, the stochastic versions are there. So the trick that I'm going to make is that I'm going to assign x1 and x2 as the x variable, as if it's this concatenated quote unquote vector or object. And then we're going to put the calligraphic x, which is the domain, all right? So in general, a joint domain constraint is broader. Note that in the min-max case, there's a split domain, all right? Now, what I'm going to also do is I'm going to define this gradient or vector field, which is gradient with respect to x1f, gradient with respect to, so actually, let's use this. Remember, x1 and x2 are now concatenated. Okay, so given this notation, our goal, which is an important one, is find some x star, right, such that Vx star is 0. All right. Now, we're used to the critical point terminology in minimization. So this is, in the case of minimization, obviously this is, you know, find a first order stationary point, right? Now, this could be a maxima, but hopefully if we do certain things, we're going to go to a local minima, all right? Hopefully this makes sense. Now, at this point, I would like to take a bit of a twist to these stationary points. Hi, Danik. Yes.
Just a quick question. about the constraints here. Are you?
Oh yes. So I'm gonna. Okay. Very good. Very good. It's good that optimizers are in here. I'm just gonna assume away that the problem is unconstrained, because otherwise I need to define gradient mappings and the whole description becomes very complicated. So you caught me. I should have quantified that in the SQL. I'm going to assume that no constraints. In the SQL, just to highlight the concepts. Otherwise, really, the notation becomes overly complicated. The talk would be maybe twice as long.
Okay, great. Thank you.
I'm sorry. Yeah, good catch. So I'm going to inject an ordinary differential equations perspective. All right. Now, for this, what we're going to do is consider the following differential equation. We're going to have x dot d, which is, maybe I can write it first using the gradient flow, and then I'll show you the changes for the general case. All right. So this, I think this will make sense. So we have the gradient of f xt. So this is referred to as gradient flow in many places, right? So if you think about it, df xt dt is something like x dot t gradient f of x of t, which is minus the gradient norm. So this is always negative. So if you look at the evolution, so let's say you're looking at this xt, looking at the time evolution of it, it's like this particular function, almost like a Lyapunov function for this, because what you also have here is this, you have equality if and only if xt is 0. Now, in the case of the general min-max, all I do is replace this with v. All right. Now here, let's give you maybe a taxonomy of the stationary sets. All right. We're going to have invariant. Right, so an invariant set is, okay, this gradient flow, when we use V's, I'm going to refer to this as the mean dynamics, MD. So you are in a set, you apply the mean dynamics, right? You remain in the set. This is invariant sets. They're attracting, sorry, I'm having trouble with the colors. Attracting. Now, attracting sets are invariant sets. And they're attracting, meaning that it attracts the nearby orbits of the mean dynamics. Right? This is one of the things about giving talks at home. So it attracts nearby orbits of MD. And then internally chain transitive sets. These are attracting sets. And they contain, some of them do not contain critical points. So let's call this so they have spurious attractors as well. Right? Right now, I am sweeping all kinds of formality under the carpet. I think that this by itself is an interesting topic, but given the time limitation, I'm not going to go into formal definitions of these sets. Okay, now let's do the following. So I'm going to make a claim, and I'll try to argue for this claim. So I'm going to say that min-max is significantly harder than min-type problems. Right? I think this is now well understood. There's a bunch of literature. Kostas Daskalakis had a paper in 2020, and Lechter had a paper, I think it is published 21, but the preprint was in 2020. There are ways to argue that finding, for example, stationary points are p-pad complete. There are like hardness results and so on and so forth. Now, some of these constructions rely on the joint domain, not the product of domains, but we're going to let it go. But I would like to give you an intuitive explanation as to why min-max is significantly harder than minimization. Okay, so for this, I'm going to draw a curve. So this will be our minimization problem curve. So let's call this our f of x. Okay. Now, if you think about our goal, right? So our goal was to find Vx is equal to 0. So in the case of minimization, what we're trying to do is find gradient of Fx0. Again, maybe Damek can jump in and say, hey, Volkan, aren't you assuming smoothness? Right now, let's assume smoothness and focus on some of these concepts. So the points that I'm interested in can be summarized as these points, okay? And what are these points? The gradient is 0. And obviously, if you're interested in the minimization problems, this is a desirable critical point, whereas this one and this one are not desirable critical points. But how do we quantify these desirable I'm going to call stable sets? Well, if you think about it, in the minimization case, we would like to look at the second order information, and if it is positive definite, this is great. It's a Hurwitz minimizer, right? Then, so a table is coming. So this will be our min type. This will be our Minmax type. Okay. Now, how about these points? Right. So about these points. In minimization, we would like to get here. What we would like to do is avoid these unstable sets. Okay. And for this, if you think about it, what you can do is look at the smallest smallest eigenvalue of the Hessian, right? And if there is a negative eigenvalue, something like a, Okay. We have a strict saddle, right? We would like to avoid strict saddles. We would like to go to these and avoid these, right? And there are also hyperbolic saddles where the determinant can be 0 while having a negative eigenvalue, right? So hyperbolic saddle. We would like to avoid these. We don't want them, okay? Now, these concepts also generalize to the min-max problems, if you think about it, all right? Now, this desirable stable sets, we call them local Nash equilibrium. All right, and there are also equivalent unstable unstable sets, unstable manifolds, right? Like ridge manifolds and so on and so forth. Okay, there are some periodic orbits and so on and so forth. There's like a ton of examples. Now, here is the issue. In the Minimax, there's a third category that does not have an equivalent in min-type problems. These ICT sets that have spurious attractors. They are stable. So there exist sets in min-max problems for the vector field such that you're not at a critical point, and yet you remain in this particular set. And many of them are attracting. So here is the interesting facts. What we do in practice is we assume typically this exists, right? So we start by non-empty. Many optimizers begin their problems with this particular assumption, okay? Now, here's the issue. This thing is non-generic in the topological sense. So this is a theorem by Smale, 63, meaning that you perturb the problem a little bit and they disappear, okay? However, in the same sense, these spurious attractors are generic, meaning they occur very easily and quite often, right? This is Kupka, Smale-Kupka theorem, right? So the fact that you go from a min problem to a min-max problem, all of a sudden, if you look at this mean dynamics, evolution of this xt can get trapped into these spurious attractors that are nowhere critical. So this is the main difficulty, right? Now, given that I spent quite a bit of time on this, I'll try to explain how we find this and give you some of the results that we have. So hopefully so far things made sense. So how do we find ICT sets? So I'm going to talk about Robbins-Monro schemes, so RM schemes. So there's a broad class of algorithms that fit into this. In the min-max case, gradient descent ascent, extra gradient, optimistic gradient descent ascent, Popos, all kinds of algorithms that fit into this. But I think that I won't have time to explain the details of this. But here is this idea, right? So remember, so recall the mean dynamics, which is, we have x naught t, which is, sorry, xt. Now consider Rn schemes. So this is like the discrete approximation. So these are capital X's, not calligraphic capital. So just to give you the notation, so this will be the step size. And this will be our error term. All right. Now, what I'm going to do is I'm going to decompose the error term into two terms. One will be the noise term. So this will be zero mean given the filtration. So the filtration is so I'm going to call this the filtration. There are several subtleties here, but for the sake of time, so we're going to have a bias term. Okay. For the bias term, in the end, we're going to end up assuming that this goes to 0. I'm going to define two more auxiliary variables. So this mu n, which is the expectant value of Bn given the filtration, and then a sigma n squared, which is the un squared given the filtration. All right. So here's the rough statement about these Robbins-Monro schemes that are discrete in nature. So roughly speaking, right? So if the step size is small, and if this error term is well behaved, the limit Rn is equivalent to the limit of time goes to infinity mere descent dynamics. Right? This is 77, Kushner and Yin. 97 and Benaim 99. Right. So if you think about it, this is actually very interesting. So think, sorry. So if you think about it, in the case of minimization problems, suppose there is no error term. This is our negative gradient, right? This scheme basically says gradient descent, okay? If you have a stochastic oracle for the gradient, you can plug that into this error term and you can get stochastic gradient descent. And I mentioned that this actually, using this kind of a scheme, we can also characterize extra gradient, optimistic gradient, and a whole host of alternating even gradient approaches in the general minimax problem sense too, all right? This is what I mean by the Robbins-Monro-type schemes. This particular discretization approach covers a lot of algorithms with the proper changes made. Okay. So some key concepts here as well. By the way, is my speed okay, or are people following? All right. Okay, good. So some key concepts. So I'm going to define time, even though my time is incorrect. So we're going to have tau n, which is the summation of I to n gamma I. We're going to have a trajectory. So the trajectory, we're going to define it as xt, which is xn plus t minus tau n plus 1 minus tau n xn plus xn. Now this guy, oh, sorry. No, here, highlighter. This guy will be trying to approximate the continuous mean dynamics through taking our discrete samples and interpolating them with respect to the step size, right? If the step size is small, the closer, the finer the steps are, okay? So we're gonna define this other additional concept, asymptotic pseudo trajectory, or APT. So the idea is this discrete thing approximating the continuous xt mean dynamics arbitrarily well. So we're going to look at limit t goes to infinity over window sizes of some length. And what we're going to do is we're going to look at xt plus some window plus this trajectory. Right, so this psi h x t is the position of position at time t plus h of an orbit of the mean dynamics. Right, so remember this is defined through the RM, Robbins-Monro discretization. And this is the one that comes through the ODE, right? And the asymptotic pseudo trajectory idea is that this thing goes to 0. So what we're gonna show is that this thing goes to 0, hence that the XT, the trajectory that we get with the RM scheme, tracks the mean dynamics with arbitrary accuracy over arbitrary window length. All right, hence establishing this connection. All right. So here's a question, key question. So when is an RM scheme sequence and APT? All right. So when does this hold? Okay. So I'm going to introduce some assumptions. So this set A of assumptions, we're going to assume Lipschitz continuity, meaning that fx minus fx prime, we're going to have g x minus g prime. We're going to assume Lipschitz smoothness. Prime. And then what we're going to do is we're going to assume something called weak coercivity. Meaning that the problem is somewhat proper when you are outside some boundaries. Okay, so this is to avoid certain pathological cases. So this is Lipschitz continuity, Lipschitz smoothness, and weak coercivity. All right. So here are additional assumptions. So this Bn, the bias, going to 0. All right. We're going to assume this summability conditions. All right, if you remember, this thing is the expected value of the bias given the filtration, and this thing is the noise term. All right, so here's a proposition. And this is from Benaim and Hirsch. '99, and we have a slightly changed version of it with C, Mertikopoulos, and Cevher. So assume A plus B, then Xn is an APT of mean dynamics with probability 1. Probability 1. All right. Now, these conditions are not interpretable. So what we added here is this assumption C. All right. And the assumption C is a bit easier to digest. So we assume a condition on the step size. So n log n 1 plus epsilon a b epsilon. So, you know, this condition is a bit more interpretable than having these sequences. You know, satisfying these are a bit difficult to see in practice, but we boiled it down to a step size condition that kind of makes sense. All right. Okay. All right. Now, so what algorithms are RM? Okay, so stochastic gradient descent ascent is an RM scheme. I think so we saw this before, right? So this xn plus 1 is xn minus gamma n vxn. Sorry about the colors. Proximal point PPM. It's an RM scheme with a bias. So if you just look at the scheme, sorry, we have a bias term. It's an implicit scheme, by the way. Approximations of the proximal point are also RM. So some approximations of PPM, such as extra gradient, optimistic gradient descent ascent. So here, I'll just give you the extra gradient version. So you first take a gradient step and then take the gradient at the gradient step and update the point, right? There's a more elegant way of writing it, but when you write it this way, you see that there is an obvious bias, okay? And if you think about in the Minimax case, you don't need to do these updates simultaneously because V actually separates into two. Right? So if you remember, there's this, then there is that. Because again, this is not a game in the traditional sense of a game where the players play simultaneously. You have control over it. You can do one update, then the other update. And all these alternating versions are also covered. But what is interesting here is that zero order schemes also fit into RM. Okay, so I'll just mention this. So zero order schemes. So the single point approximation scheme the idea is very simple. You take xn hat, which is xn plus gamma n, some random variable on the sphere, unit sphere, with some step. And then what you do is, so this is gamma n, the dimension, so let's say the d-dimensional sphere. You evaluate the function. Now, what I've been telling you, actually, it turns out that there's a mirrored version of this mean dynamics. And by using the mirrored version, which is some ongoing work currently, you can actually capture things like EXP3, all these bandit algorithms also within the RM framework. So some of the things that I will just tell you to wrap things up also apply there, okay? But I think we don't have enough time to get into the details of this. So let's wrap things up in one slide, all right? So what does it all mean? Okay, so in terms of avoidance, we have a very nice result. Okay, so theorem, call it avoidance. Okay, so let's assume so one, F is Lipschitz continuous and Lipschitz smooth. Let's take a step size. Gamma n 1 over n to the p. P is element of 0, 1. And let's assume this noise, let's assume there's zero bias. So here's a simplified one. This noise term is uniformly exciting, meaning it's like isotropic, but it does not need to be the same strength in every direction. So uniformly exciting. In this case, the probability that this xn, this RM schemes, will go to an unstable set is 0. Meaning these stochastic schemes, they will not go to these unstable points. They will just avoid them. So things like strict saddles, maximums, they will just avoid them in minimization, right? But also in min-max. Okay, here's another theorem. Right, so convergence. So this is HMC 20, HMC 20. Now we're going to assume A plus B. If you remember, this A had Lipschitz continuity, Lipschitz smoothness, and weak coercivity. And B was this summability conditions, which you can replace them with step size conditions, okay? So let's say S is an attracting set, right? So for all alpha greater than 0, probability that Xn will go to an attracting set, given that X0 is in the neighborhood of S is greater than 1 minus alpha, meaning these algorithms will go to an ICT set. However, the issue here is that ICT sets could be spurious, especially in the Minimax. In minimization, they don't exist. These spurious sets do not exist. But in Minmax, you cannot avoid them, right? So this is actually an issue. In the min case, we have a slightly stronger result. So this is okay. So this is from NeurIPS. If you have the same conditions, so maybe I just lasso them. Copy, paste. So if you have the same conditions, right? Interestingly, you can just set P is equal to 1, then SGD will converge with order 1 over n rate in objective value. So meaning that if you look at the non-convex literature, people like to do these faster decay rates on step sizes. It looks like it actually does make sense from the theoretical perspective. And with this, I'm going to end the talk. But what I did is also, okay, so sorry, talks. So I would like to show you some of these attractors. So here's an example of a Minimax problem. The form of this can be found in our paper. There are two ICT sets that are spurious here. So this is inner circle and this outer circle. If you initialize the algorithm anywhere in the outer circle, you come to this inner circle. So the algorithm we ran here is the stochastic gradient descent ascent. I have pictures for the extra gradient and all the other algorithms. What is interesting is that the spurious attractor here is a repelling one. So if you initialize it within the inner circle, so here, you will go to this. And the only way to reach to this min-max point is to initialize it within this inner circle. All right. So this is really, I mean, it shows you the difficulty of such problems. There are many traps. So this is, I mean, an example of a similar kind. So if you initialize it here, the algorithm finds it to the min-max point. If you initialize it here, it goes out. If you initialize it here, it goes here. And once it gets in this, they just remain circling around without realizing that they are nowhere critical, right? And here, if you do averaging of the sequence, so this blue line is the averages, you may get closer to the min-max point, but not necessarily. Things depend on whether or not there are more, like geometrically, there are different things. So I don't know if averaging probably helps. All right, with that, I will end. So if you have questions, I'm happy to answer.
So people might go since it's 10, but we can stay for a few questions. So I have, I'll start with one quick question.
Go for it.
And so in this picture you showed, you were doing just the like simultaneous gradient descent, right?
So here's the extra gradient.
Yeah, but you also said the negative gradient, sorry, negative momentum fits in this range of schemes, right? So negative momentum is what we usually use to avoid this.
I did not say negative momentum. I did not. So you actually pointed out something critical, right? Negative momentum. I mean, you could say maybe here the negative momentum might, but maybe not.
Okay, it doesn't fit into RM. I thought you said it does.
No. I didn't say. None of the accelerated schemes fit into this. But what I said is that the mirrored descent dynamics, where you have a mirror map, some of the zero order schemes also fit, like EXP3 and so on and so forth. Alternating schemes fit into this, but I mean, you need to look at Boyd-Candes for the positive momentum case, right?
So what is the thing you called optimistic?
Optimistic mirror descent ascent.
Yeah.
So it
what
is
that, dynamics that what was that?
So in the optimistic descent ascent, what you do is this. So this is the optimistic gradient descent ascent. There are half shifted versions so that you only do one gradient computation, so on and so forth. There are a variety of ways of writing these kind of schemes. This is more like the reflected forward backward scheme. There, you can also do the following, which is the forward reflected backward, reflected forward backward, and then forward reflected backward. All of these schemes fit into the RM template that I mentioned. So this is the optimistic version.
We have another question. Please go ahead.
Go ahead.
Yeah, can you hear me?
Yes.
Okay, so I have a question about the last avoidance theorem. Yeah, it's this one. As you indicated, the bias can be non-zero. I mean, so for example,
bias needs to be going to zero.
Okay, so for example, if the step size is like 1/n, then I mean, if we know that the bias will tend to zero, then we will have same.
The bias term times the step size needs to be summable.
Okay, right? So that's the only assumption we need.
That is the assumption.
Okay. Okay, I see.
But it's this.
Okay. Yeah. Thank you.
No problem. I mean,
I had a question.
Go for it.
Sure. So, like in this kind of talk, you're focusing on finding local Nash equilibria, but in some of the like motivating examples, it might be more natural to think of them as problems of finding like Stackelberg equilibria. So do you have a sense of like how this kind of analysis changes if you think about it in terms of finding local Stackelberg equilibria?
So if you remember the way I set things up, I eluded connections to game theory, but what I described so far, it's not yet games, right? Now, I think it is interesting to look at online learning in games and think about, let's say, variationally stable solutions and the twists that like the Stackelberg twist, Elliott-Carlton games, alternating game twists. So this is something that we're looking at. I think Mila group had something on Stackelberg characterizations. I haven't gone through the details of that, but certainly interesting. So what I described here, even though it sounds like this whole broader framework, it's not yet there. It's just these Robbins-Monro-type schemes that have been, that we use, like stochastic gradient descent ascent, alternating versions of gradient ascent descent, or even the versions where one of the players take more iterations than the other player takes, are covered. What is not covered is maybe different time scales. So two different time scales, and even oscillations like the step size increasing, decreasing, increasing, decreasing. So there are cases that are not covered. But what the result says is that the typical users of these algorithms, they cannot avoid these spurious attractors in Minimax problems, right? Hence, it tells you that things like GAN training, you can do additional iterations in the discriminator. You don't necessarily avoid these spurious attractors. Now, let's say the width of the spurious attractors turns out to be related to something I think Damek is working on this week, convexity. If you have some additional structure on the problem, then by doing more iterations in the inner problem, you end up making certain things like these limit cycles, you decrease their widths and so on and so forth. So there are interesting things that are going on. And these are the kind of things that we are also looking at. Yeah? All right. So thanks all. I hope the talk was clear. I went a bit slow. I think I highlighted things that I wanted to highlight.
No, it was good. It was important to set it up.
All right, see you. Thank you. Bye.